Poisson's equation. Okay, so we know from the Gauss law del dot d bar is equal to the charge density rho v, right? Now here d bar you can write as epsilon E bar. So this is equal to rho v, and once again the electric field we can write in terms of the potential as the negative gradient of potential. So del dot epsilon minus del v is equal to rho v. Okay, so from here you can write del square v is equal to minus rho v by epsilon. Okay, so this is called as the Poisson's equation, but one thing you have to remember is here epsilon we have simply taken out of the divergence, right? So this is only possible if epsilon is same at all points in the region. Okay, so it's basically a constant. So taking it out will not make a difference. So that is how we can get this equation. Okay, so this is only for homogeneous medium. That is, epsilon is same at all the points in the region. Okay, so this is the Poisson's equation. Now if you take the Laplace equation is directly we can get from the Poisson's equation. Okay, so the Laplace equation just means that del square v is equal to 0 in a charge free region, as simple as that. Okay, so why? Because in a charge free region, charge free means rho v is 0, there is no charge, right? In that case what will happen? Del square v will be 0. Okay, so this is the Laplace equation. And lastly we have something called as the uniqueness theorem. So this is not required in much detail as of now. It just means that the solution to Laplace equation is unique. So there are different approaches to solve the Laplace equation. So whichever approach you go, the final solution you are going to get the same. So that is the uniqueness theorem.